Assalamu alaikum all. Can you hear me? Yes, what about others? Okay, good. Yeah, regarding your study guide, as I have discussed with you in our face-to-face lecture, inshallah, I'll talk to Dr. Alam, and whatever will be his decision, I will inform you, inshallah. We will try our level best to help you out in every possible way. So, don't worry about it. I will talk to him and then let you know. So, this week is week 5, and we have chapter number 6 and chapter number 7 this week. Chapter 6 we have already discussed, and now we will discuss chapter 7, in which we will be going to study about SNMP v3. As I have told you that the security feature was lacking in SNMP v2. So in SNMP v3, the key feature is the improved security feature. So the configuration can be set remotely with the secured communication that protects against modification of information by using encryption schemes. So encryption, you know that we have plain text, and that plain text is converted into ciphertext at the sender side, and at the receiver side ciphertext is converted back to plain text. So this is called decryption. So here we have encryption schemes. Now in this protocol, it also tries to ensure against malicious modification of messages by reordering and time delaying of message streams, as well as it protects against eavesdropping of messages. Now the access policy used in SNMP v1 and SNMP v2 is continued and formalized in the access control in SNMP v3, designated as VACM. The SNMP engine defined in the architecture checks whether a specific type of access, that is read, write, create, or notify to a particular object instance is allowed or not. So these are the key features you can see over here. These are the key features that are there in SNMP v3. So apart from security feature, as you can see, this point, security feature, what we have modularization of architecture and documentation. So the design of architecture integrated SNMP v1 and SNMP v2 specifications with newly proposed SNMP v3. So this enables continued use of legacy SNMP entities along with SNMP v3 agents and managers. So this is a good news, as there are 10,000s of SNMP v1 and SNMP v2 agents in the field. So an SNMP engine is defined with explicit subsystems that include dispatch and message processing functions. It manages all 3 versions of SNMP to coexist in our management entity. So we have application services and primitives have been explicitly defined in SNMP v3. This formalizes various messages that have been in use in earlier versions. Here you can see the documentation. We have numerous SNMP documents that have been organized by IETF, that is Internet Engineering Task Force, to follow a document architecture. The SNMP document architecture addresses how existing documents and new documents could be designed to be autonomous. and at the same time they integrated to describe different SNMP frameworks. So it can be correlated. So two sets of documents are of general nature. One of them is the set of documents on roadmap, applicability statement, and coexistence and transition. The other set of documents, SNMP Frameworks, comprises three versions of SNMP. An SNMP framework represents the integration of a set of subsystems and models. Now here in this table, it shows SNMP V3 RFCs. So RFC 3410, as you can see, it provides an overview of SNMP V3 framework. Then we have RFC 3411. It presents an overview of SNMP V3. It defines vocabulary for describing SNMP management frameworks and an architecture for describing the major portions of SNMP management framework. Next we have RFC 3412. It describes message processing and dispatching for SNMP messages. Procedures are specified for processing multiple versions of SNMP messages to the proper SNMP message processing models, that is MPM, Message Processing Model, and for dispatching packet data unit to SNMP applications. A new MPM for version 3 is proposed in this document. Next we have RFC 3413. It defines 5 types of SNMP applications. The first one is command generators. Then we have command responders, notification originators, notification receivers, and proxy forwarders. It also defines management information base, that is MIB modules, for specifying targets of management operations, for notification filtering, and for proxy forwarding. Next we have RFC 3414. It addresses user-based security model, that is USM, for SNMP V3 and specifies the procedure for providing SNMP message level security. MIBs for remotely monitoring and managing configuration parameters are also specified. Then we have RFC 3415. It is concerned with access control model that deals with the procedure for controlling access to management information. MIB is specified for remotely managing the configuration parameters for the view-based access control model, that is VACM, View-Based Access Control Model. Then we have RFC 3416. It defines version 2 syntax and procedures for sending, receiving, and processing of SNMP PDUs, that is packet data units. Next, RFC 3417. It defines the transport of SNMP messages over various protocols. Now, can you tell me, when we are talking about transport mapping, what does it mean? What is transport mapping? We have discussed in our face-to-face lecture this week. Okay, using UDP. So this UDP is used in SNMP version 1 also, but here we are talking about transport mapping. So what's the difference? In SNMP V1 also we are using UDP. In SNMP V2 we say that there is a transport mapping. What does it mean? Yes, good, very good. That means we are using other protocols also in addition to UDP. But in version 1, this option was not there. We were using only UDP because it is connectionless protocol. Next we have RFC 3418. It describes the behavior of an SNMP entity. And lastly, we have RFC 3584. It describes the coexistence of SNMP V3, SNMP V2, and SNMP V1. Virtual database? What do you mean? MIB. Yes, MIB is a virtual database. It is management information base. So this database is virtual. Now it also describes how to convert MIB modules from SMI V1 format to SMI V2 format. So in the last SNMP version 2, we have seen that we have moved on to version 2 format of SMI. So it also describes how to convert MIB modules from SMI V1 format to SMI V2 format. Now this shows SNMP V3 architecture. An SNMP management network consists of several nodes, each with an SNMP entity. They interact with each other to monitor and manage the network and resources. The architecture of SNMP entity is defined as the elements of an entity and the names associated with them. So there are three kinds of naming. First is the naming of entities. Secondly, naming of identities. And thirdly, naming of management information. Here you can see SNMP entity is basically a node with an SNMP management element, and that can be an agent or manager or both. Now first of all, we will see at the elements of entity, including its naming. So the elements of architecture associated with SNMP entity comprises of SNMP Engine, and a set of applications. The SNMP engine, which is named as SNMP Engine ID, comprises a dispatcher, message processing subsystem, security subsystem, and an access control subsystem. Now, SNMP engine, as you can see in figure 7.2, this is SNMP engine. An SNMP entity has one SNMP engine, which is uniquely identified by its name, that is SNMP Engine ID. This one. The SNMP Engine ID is made up of octet strings. The length of ID is 12 octets for SNMP V1 and SNMP V2 and is variable for SNMP V3. Now you can see this figure 7.3. The first 4 octets in both formats are set to binary equivalent of agent's SNMP management private enterprise number. The first bit of the 4 octets is set to 1 for SNMP V3 and 0 for earlier versions. For example, if we have networks that have been assigned enterprise 696, so the first 4 octets will read the 5th octet for SNMP V1 and SNMP V2 indicate the method that the enterprise used for deriving SNMP Engine ID, and 6 to 12 octet functions of the method. For a simple entity, it could be just IP address of the entity. The 5th octet of SNMP V3 Engine ID indicates the format used in the rest of the variable number of octets. Now here in table 7.2, you can see we have dispatcher, we have message processing subsystem, security subsystem, and access control subsystem for SNMP engine. Now see the dispatch subsystem. There is only one dispatcher in an SNMP engine, and it can handle multiple versions of SNMP messages. It does 3 sets of functions. Firstly, it sends the messages to and receives the messages from the network. Secondly, it determines the version of the message and interacts with the corresponding MPM. And thirdly, it provides an abstract interface to SNMP applications to deliver an incoming PDU to the local application and to send a PDU from local application to a remote entity. Now the three separate functions in the dispatcher subsystem are accomplished by using firstly a transport mapper, secondly a message dispatcher, and thirdly a PDU dispatcher. So the transport mapper, what it does, it delivers the message over the appropriate transport protocol of the network. The message dispatcher routes the outgoing and incoming messages to the appropriate module of the message processor. Now, if a message is received for an SNMP version, which is not handled by the message processing subsystem, what it will be done? It will be rejected by the message dispatcher. The PDU dispatcher within an SNMP entity handles the traffic routing of PDUs between applications and the message processor model, MPM. Now next we have message processing subsystem. The SNMP message processing subsystem of an SNMP engine interacts with the dispatcher to handle version-specific SNMP messages. Now, it contains one or more than one MPMs, and the version is identified by the version field in the header. Next, we have security subsystem and access control subsystem. The security subsystem provides security services at the message level in terms of authentication and privacy protection, and the access control subsystem provides access authorization service. Now next we have application module. This application module is made up of one or more applications, which comprises of command generator, notification receiver, proxy forwarder subsystem, command responder, notification originator, and others. Now the first three applications are normally associated with an SNMP manager, and the last two with an SNMP agent. So the application module may also include other applications, and it is indicated by other box. So we have discussed about dispatcher, message processing subsystem, security and access control. Then we have seen the application also, command generator, notification receiver, proxy forwarder, command responder, and notification originator. Now we have abstract service interface. Now the subsystems in an SNMP entity communicate with each other across an interface. A subsystem providing a service and the other using the service. So we can define a service interface between the two. If the interface is defined such that it is generic and independent of specific implementations, it becomes a conceptual interface, and it is termed as abstract service interface. Now these abstract services are defined by a set of primitives that define the services. In this figure, we can see we have a subsystem A, which is sending a request for service using the primitive AB to subsystem B. Now the primitive AB is associated with the receiving subsystem B, which is the one that is providing the service in this figure. Now A primitive has in and out as operands or parameters, which are the data values. This is the in, this is the out. Now these are indicated by A1, A2 and B1, B2 respectively. The in parameters are the input values to the called subsystem from the subsystem calling for service. The out parameters are the responses expected from the called subsystem to the calling subsystem. Now the out parameters are sent unfilled in the message format by the calling system and are returned filled by the called subsystem. When the calling subsystem expects a response from the called subsystem, there are directed messages in both the directions with a two-directional arrow coupling the two. Now in this case, the primitive AB is only directed in the forward direction. Now in addition to returning the out parameters, the called subsystem could also return a value associated with the result of the request in terms of status information or result. Now because of execution of primitive AB, subsystem B may initiate a request for service from another subsystem, subsystem C, using primitive BC over the abstract service interface between subsystems B and C. Now except for dispatcher, the primitives are associated with the receiving subsystem. Dispatcher primitives are used in receiving messages from and to the application modules, as well as registering and unregistering them, and in transmitting and receiving messages from the network. Now see this figure. This is an example of application command generator sending a request, send PDU, and it is destined for a remote entity to the dispatcher. Now the dispatcher, after successful execution of the service, requested and sending it on the network, it returns to the application send PDU handle. The send PDU handle will be used by the command generator to correlate the response from the remote entity. There are no out parameters to be filled in this primitive except the status information. So the command generator does accept the status information, and hence the coupling arrow, which is indicated in this figure, now the dispatcher sends an error indicator instead of send PDU handle for the status information if the send PDU transaction is a failure. The dispatcher also generates a request to the MPM, that is prepare outgoing message. This one. The prepare outgoing message has both in and out parameters, and information flows in both the directions. So the numerous in and out parameters associated with primitives are not identified in the figure for the sake of simplicity. So now we have this table. It lists the primitives that are being served by the dispatcher, message processing subsystem, security and access control subsystem. Now here we have module dispatcher. The primitive is send PDU, and the service provided is request from application to send a PDU to a remote entity. And so on. Now this is the command responder. Basically, it processes the get and set request that are destined for it and is received from a non-authoritative remote entity. So it performs the appropriate action of get or set on the network element, and it prepares a get response message and sends it to the remote entity that made the request. So this is shown in this figure. Now here, the top and bottom half processes run on two remote objects. And the command responder is in the management agent associated with the managed object. Now before the get request could be processed by the command responder application, the context that the SNMP engine is responsible must register with the SNMP engine. It does this by using register context engine ID. Now once this is in place, the get request is received by the dispatcher. Data elements are prepared by MPM. Security parameters are validated by SM, and the process PDU is passed on to the command responder. Now this set of processes is presented in the top half. Now once the request is processed by the command responder, it prepares the get response message as shown in the bottom half. Now the message is passed to the dispatcher using the return response PDU. The MPM prepares the response message, SM performs the security functions, and the dispatcher transmits the get response message on the network. Now here we have notification originator. This is the application which generates either a trap or an inform message. So its function is somewhat similar to the command responder, except that it needs to find out where to send the message and what SNMP version and security parameters to use. Further, the notification generator must determine the context engine ID and the context name of the context that has the information to be sent. It obtains these data using newly created MIBs for the notification group and the target group, as well as using other modules in the system. The notification group contains information on whether a notification should be sent to a target, and if so, what filtering should be used on the information. The target that the notification should be sent to it is obtained from the target group. Then we have notification receiver. This notification receiver application receives SNMP notification messages. It registers with SNMP Engine to receive these messages, just as command responder does to receive get and set messages. Then we have proxy forwarder. This application performs a function similar to that of proxy server. The proxy definition is restricted in SNMP v3 specification. Here, the term proxy is used to refer to a proxy forwarder application that forwards SNMP requests, notifications, and responses without regard for what managed objects are contained in those messages. Now, non-SNMP object translation does not fall under this category. The proxy forwarder handles 4 types of messages. Firstly, messages generated by command generator. Secondly, messages generated by command responder. Then, notification generator. And finally, those that contain a report indicator. So the proxy forwarder uses the translation table in the proxy group MIB created for this purpose. This is SNMP version 2 MIB. Now this is SNMP version 3 MIB. Now the new objects which are defined in SNMP v3 follows the textual convention specified in SNMP v2, and we can refer to RFCs which were listed in table 7.1. Just few minutes back we have seen that table. For complete details on managed objects and MIBs in SNMP v3, we will address a subset of MIBs here. Now here in this figure, in this figure, we have MIB of the new object groups. They are nodes under SNMP modules 1.3.6.1.6.3. Now there are 7 new MIB groups. Now SNMP forward MIB node 10 under SNMP module describes the SNMP management architecture. The MIB group SNMP MPD MIB node number 11 identifies the objects in message processing and dispatching subsystems. Then we have 3 groups defined under SNMP modules for applications. They are SNMP target MIB node number 12 and SNMP notification MIB node number 13 and SNMP proxy MIB node number 14. So the first 2 are used for notification generator. The SNMP target MIB defines the MIB objects which are used to remotely configure the parameters used by remote SNMP entity. And the SNMP target address table, which is SNMP target objects group, contains the addresses to be used in the generation of SNMP messages. Now let's see. SNMP V3 target MIB. This is SNMP V3 notification MIB. Now these are the security threats. Now one of the main objectives in developing SNMP V3 is the addition of security feature to SNMP management. Now authentication and privacy of information as well as authorization and access control, they all are discussed in SNMP V3 specifications. Now SNMP V3 architecture permits flexibility to use any protocol for authentication and privacy of information. Now the IETF SNMP V3 working group has specified a USM for its security subsystem. It is termed as user-based as it follows the traditional concept of a user identified by a username with which to associate security information. Now here we have security threats. So 4 types of threats exist to network management information while it is being transported from one management entity to another. So firstly is the modification of information. Then we have masquerade, then message stream modification and disclosure. Now the first one is modification of information. It is the threat that some unauthorized user may modify the content of message while it is in transit. So data contents are modified, including falsifying the value of an object. It does not include changing the originating or destination address. the modified message is received by entity B, which is unaware that it has been modified. So for example, the response by an SNMP agent to a request by an SNMP manager could be altered by this thread. Then next we have masquerade. This is when an unauthorized user sends information to another, assuming the identity of an authorized user. So this can be done by changing the originating address. Using the masquerade and modification of information, an unauthorized user can perform operation on a management entity which he or she is not permitted to do. The SNMP set operation should be protected against the attack. The SNMP communication uses connectionless transport protocol such as UDP. This means that the message could be fragmented into packets, with each packet taking a different path. So the packets could arrive at the destination out of sequence and have to be reordered. So the threat here is that the intruder can manipulate the message stream, that is message stream modification, and maliciously reorder the data packets to change the meaning of the message. For example, the sequence of data of a table could be reordered to change the values in the table. The intruder could also delay messages so that those messages arrive out of sequence. The message could be interrupted, it can be stored and replayed at a later time by an unauthorized user. And finally, we have disclosure of management information. The message needs to be intercepted for this, but just eavesdropping. For example, the message stream of accounting could be monitored by an employee with TCP/IP dump procedure, and then the information could be used against the establishment. So there are at least two more threats that will be considered as threats in traditional data communication, but the SNMP SM has classified them as being non-threats. So the first is denial of service. When an unauthorized user is denied service by a management entity, it is the responsibility of the protocol to address this issue. The second threat that is not considered a management threat is traffic analysis by an unauthorized user. So it was determined by IETF SNMP V3 working group that there is no significant advantage achieved by protecting against this attack. Now next we have security services, role of SNMP engines, SNMP V3 message format, user-based security model. Okay, this is very important, user-based security model. So this is all. Now the rest of the slides you have to study yourself because we don't have time now. Go through them. If you have any question, you can ask in both face-to-face lecture and virtual lecture. You can come to my office. I have office hours. In that office hour, you can come and discuss if you have any problem. So this is all about chapter number 7. Next week, inshallah, we will be discussing chapter number 8. Yes. Yes, please. Any question? The midterm up to what chapter? See, week 7, until week 7, we will discuss chapter 9. Till chapter 9. Next week, inshallah, we will be discussing chapter number 8. That is week 6. And week 7, we will be discussing chapter number 9. And week 8 is your midterm week. So it will be up to chapter number 9. Chapter 9. Up to chapter number 9. So we have 2 more chapters that will be covered in the coming 2 weeks. So far, it is up to chapter number 9. If there will be any modification, I will inform you, inshallah. Yes, from 1 to 9. See you in next face-to-face lecture then. Till then, take care all of you. Assalamu alaikum.